4:31 in the morning, January 17th, 1994. The San Fernando Valley is asleep. Then, without warning, the ground accelerates upward. The force hits 1.8 G, nearly double the force of gravity. This is not the rolling motion Californians are used to. It is a violent punch from directly below. In an instant, the power grid fails, and the entire Los Angeles basin plunges into absolute darkness before the shaking even stops. Engineers believed the city was ready for the big one. They were confident in their codes, but they were wrong. The $20 billion that followed was not just for repairs. It was the price of learning that the city was built on outdated assumptions. The violence came from a blind thrust fault. Unlike the famous San Andreas, which leaves a visible scar on the surface, this fracture was buried deep underground. It had been silently storing energy for centuries, invisible to geological maps, hiding directly beneath the suburban grid. When it finally ruptured, it did not just shake the ground, it deformed the entire valley. At Newhall Pass, where Interstate 5 meets Highway 14, the infrastructure faced a test it had failed before. The Gavin Canyon overcrossing had collapsed during the 1971 Sylmar earthquake. It was rebuilt, but the design flaws remained. As the ground heaved, the southbound lanes snapped. In the pre-dawn darkness, LAPD motorcycle officer Clarence Wayne Dean was reporting for duty. He was riding south on Highway 14, likely seeing only the black horizon. He could not see that the freeway ahead of him had vanished. He rode off the edge of the collapsed structure, falling 30 feet into the wreckage below. His death was not an accident of nature. It was a failure of engineering. The culprit was column shear. The massive concrete pillars holding up the freeway bridges looked strong, but they were brittle. Inside the concrete, the vertical steel bars were held together by horizontal ties. In 1994, those ties were spaced too far apart. Under the intense vertical acceleration of the quake, the concrete core had nowhere to go. It exploded outward, crumbling like dry chalk. Without that core, the steel buckled, and the heavy road deck slammed into the ground. Miles away, the Santa Monica Freeway, Interstate 10, suffered the same fate. This is the busiest freeway in America, the primary artery connecting West Los Angeles to downtown. At La Cienega Boulevard, the bridges failed catastrophically. The collapse did not just block traffic, it severed the economic lifeline of the region. Millions of commuters were suddenly cut off. The tragedy is that this vulnerability was not a mystery. Caltrans engineers knew about the danger of non-ductile concrete columns. They had identified the risk after 1971 and had even started a retrofit program. But the program was slow, underfunded, and politically unsexy. They were in a race against geology. And on that January morning, the geology won. The freeways were the most visible scars, capturing the news cameras. But while the concrete lay in ruins, a more dangerous failure was hiding inside the buildings that remained standing. While the broken freeways dominated the morning news cycle, a more intimate and terrifying tragedy was unfolding on Reseda Boulevard. The Northridge Meadows apartment complex looked like thousands of other buildings in the San Fernando Valley. A 3-story stucco building, built in the 1970s. But it harbored a structural defect that engineers call a soft story. To maximize space for cars, the ground floor consisted of open carports held up by slender wood posts, while the heavy apartments above were stiffened with walls. There was a mismatch in rigidity. When the earth punched upward, the heavy upper floors moved as a solid block. The flimsy ground floor could not handle the lateral shift. It did not just crack, it folded. In seconds, the building knelt down. The second floor slammed into the pavement, obliterating the parking level and the apartments directly adjacent to it. 16 people were killed, most of them crushed in their beds before they could even wake up. It remains one of the deadliest structural failures in modern California history. The mechanics were simple. You cannot put a heavy, stiff box on top of a weak, flexible table and expect it to survive a kick from below. That risk was known, but it had been tolerated as an acceptable gamble. Northridge called that bluff. Yet, as rescue crews worked through the rubble of wooden apartments, a far more complex crisis was brewing in the steel towers that defined the Los Angeles skyline. For decades, engineers believed that welded steel moment frames were the invincible backbone of modern construction. The theory was based on the material properties of steel itself. Steel is ductile. Unlike concrete, which cracks, or wood, which snaps, steel is supposed to yield. It stretches and bends, absorbing the kinetic energy of an earthquake like a massive shock absorber. A steel building might come out of a quake, leaning or deformed, but it would never break. That assumption shattered along with the ground. In the weeks following the quake, inspectors began peeling back the drywall and fireproofing in buildings that, from the outside, looked perfectly fine. What they found inside sent a shockwave through the global engineering community. The connections where the horizontal beams met the vertical columns, the pre-Northridge connection, had not stretched. They had fractured. The welds connecting the thick steel flanges had cracked like glass. In some cases, the columns themselves were torn apart by the stress. The energy of the quake had not been absorbed by the bending of the beams. It had attacked the joints directly. This was a brittle failure in a material chosen specifically for its flexibility. It was a catastrophic blind spot. These buildings had not collapsed, but they were structurally dead. The skeleton was broken. Hundreds of modern buildings, the places where people worked and lived, were suddenly revealed to be ticking time bombs. The industry had to face a terrifying reality. The standard way of building skyscrapers in earthquake country was fundamentally flawed. The city could not just patch the cracks. The entire philosophy of how to connect steel had to be rewritten from scratch. The financial impact was staggering. Northridge caused $20 billion in direct damage. Adjusted for inflation, that figure today would exceed $40 billion. It was the costliest natural disaster in United States history at the time, bankrupting smaller insurance carriers and forcing the creation of the California Earthquake Authority. But the check written for repairs was actually a tuition payment. Los Angeles had just received a crash course in near-source physics. Before 1994, seismic maps largely ignored the specific violence of faults located directly under urban centers. They averaged out the risk. Northridge proved that when you are right on top of the rupture, the ground motion contains a massive fling pulse. a single coherent wave of energy that slams into a structure with high velocity. The code had to be updated to account for these killer pulses. The most dramatic change happened in the steel industry. The pre-Northridge welded connection was effectively banned. Engineers developed a counterintuitive solution to save the buildings. They weakened the beams on purpose. By deliberately cutting away a section of the steel flange near the connection, a shape that looks like a dog's bone, they force the beam to yield at that specific spot. This dog bone cut acts as a fuse. It ensures that the beam bends and deforms safely away from the brittle weld, protecting the critical connection to the column. If you see a steel tower going up in Los Angeles today, that geometry is hiding inside the walls. At the same time, Caltrans launched a frantic political and engineering campaign to armor the state's bridges. They wrapped thousands of concrete columns in steel jackets. These casings provide the confinement that the old rebar ties could not. Now, when the concrete core tries to explode outward under pressure, the steel jacket holds it tight, maintaining the column's strength even as the earth tries to shear it in half. But the ultimate proof of concept came from the USC University Hospital. While other medical centers in the valley were evacuating patients through dark, debris-strewn hallways, the USC facility remained fully operational. It did not just survive, it barely felt the quake. The building sat on base isolators, massive rubber and steel bearings that decoupled the structure from the ground. When the earth moved 18 inches, the hospital stayed still, floating above the violence. This cemented a shift in philosophy. The goal moved from life safety, building a structure that does not kill you when it dies, to resilience. The new standard was a building that could take the hit and open for business the next morning. Northridge ended the era of engineering arrogance. It proved that building codes are reactive documents, written in the debris of the failures that came before. We learned that nature always has more energy than we have concrete. Yet the threat lingers. Thousands of soft-story apartments and non-ductile concrete buildings still stand in Los Angeles, waiting for the retrofit funds that have not come. The geology has not changed, only our understanding of it has. If you want to understand the invisible infrastructure holding your world together, subscribe to The Fault Line. We investigate the cracks in the system before they break.